All right, good afternoon, everyone. Let's get started. So today we are going to talk about EfficientML.ai, Lecture 11, TinyEngine and Parallel Processing. So the Lab 1 score of Lab 1 was released, so feel free to check it out. It's been fully graded. So this lecture is quite important for our last lab, which is Lab 5, to deploy a large language model locally on a laptop. So it's a pretty important lecture. So today we are going to first talk about some constraints of Edge AI, why they're essential, and then a lot of parallel computing techniques, which is the focus of today's lecture, including loop optimization, multi-threading, SIMD programming, and CUDA programming. After that, we're going to talk about several inference optimizations, such as image to column, in-place stepwise convolution, how to choose the best memory layout, and also using the Winograd convolution. So very briefly, a recap of the motivation, which is Edge AI. Edge AI has a lot of applications, such as here in smartphones, in the vehicles, in robots, in the smart office, etc. But Edge AI has limited computational resource constraints. So here we compare the cloud GPU, the Apple M2, the desktop, the mobile device, and also the microcontrollers. So the memory for GPU, 80 gigabyte, for the M1, M2, maybe 100 gigabyte, mobile device, 8 to 24 gigabyte, but microcontroller has only 300 kilobyte. And also the compute power, 2000 TOPS per second, 30 TOPS per second, and only several hundred million ops per second. So several orders of magnitude difference, which motivates us to efficiently program these devices. So here is a comparison of the computational resources comparing our MacBook, MacBook Pro versus a microcontroller. Okay, so here, this is the microcontroller, this is the MacBook Pro, and this is the difference. So we categorize them by the number of CPU cores, 1 versus 20. Okay. The clock rate is also differ a lot. 200 megahertz versus 3 gigahertz. Microcontroller has no GPU core, no neural engine core. L1 cache is really small, only 8 kilobytes. No L2 cache or 3 cache, versus the MacBook CPU has a lot of L3 cache. The memory capacity a few hundred kilobyte versus 64 gigabytes. Storage also differ a lot, etc. And what's sad here is there's no operating system, so you have to manage the memory by yourself. And here is the memory hierarchy, comparing the speed, the latency, and also the capacity as you go from the register, L1, L2 cache, to memory, to the storage. We get a larger and larger capacity from a few hundred kilobytes all the way to a few terabytes. Memory here can go to actually a few, actually much larger than this on the server. And the latency also gets longer. Okay, so you don't want to go to DRAM. You want to stay in the cache as much as possible. So that's some recap of what we learned in 6.191 in the computer architecture class, which is a prerequisite. So given these constraints, we want to efficiently program these processors such that it can efficiently handle this neural network workload. So let's talk about how to exploit the parallelization to accelerate the neural network inference and training. So here are the 4 blocks we are going to discuss today. You are going to implement every technique here in Lab 5. So pay attention to these techniques. We are going to have a real-world implementation. So we'll start with loop optimization. Okay. So there are several for loops. A matrix multiplication is basically 3 for loops. A convolution is basically 6 for loops. The optimizing loop is very essential for parallel processing. And our main target is to optimize for the locality, okay, cache locality. and reduce the branching overhead. Okay, try to avoid the branching. So we'll cover loop reordering, hiding, unrolling. And next, we are going to talk about SIMD instructions, single instruction, multiple data, and also multi-threading, and finally CUDA programming. So here we are going to start with the first one, loop reordering, to optimize the locality by reordering the loop orders or the sequences of the loops. So let's see this example where we have a naive implementation of a matrix multiplication. The dimension is n by n times n by n matrix. You get another n by n matrix. You have 3 for loops, ijk, cij plus equal to aik times bkj. Okay. So what is the order that we access the 2 matrices? So for the A matrix, we traverse them in the ik manner. Okay, I is outside, k is inside, so we go to k first, then I, k first, and then I. But for the B matrix, okay, for the B matrix, the order is k, kj, and k is actually inner, j is the outer. So actually, we are doing it in the vertical manner. Okay, so they are not stored contiguously in the memory. For example, here B00 and B10, they are not continuous in the memory. So you fetch, when you are fetching B00, you fill in the cache line containing B00, 01, 02, which you should have learned those in our prerequisite 6.191 in the computer architecture course. So we'll not go deeper into what the cache line is, assuming you already have those background in the prerequisite. So it will bring in B00, B01, B02 in the cache line. But B10 will not be in the cache line of B00. So it has very poor data locality for the B matrix. So we can reduce the cache miss by reordering the loop for B. For example, rather than using ijk, we can do the loop order of ikj. And let's see what is the order now for the B matrix. Okay, so this is before, this is after. Before we have ijk, after we have ikj. Okay, so previously A is horizontal, B is vertical. Now A is horizontal, B is also horizontal. Because here we are accessing bkj, K is the outer loop, J is the inner loop. Therefore, the access pattern will be horizontal. Okay, and the horizontal values are stored in the same cache line, improved its locality. So what is the catch here? The locality for what about the locality for C? Did it get better? Did it get worse for the C matrix? Yes. Yes, exactly. Using the previous approach, C is ij, so they're in the outer loop. Okay? So we can just focus on computing on one C, and all the A's, all the B's associated with that particular C element. Once it's done, we move forward to the next C. So very good output locality. But here we have many partial results for C. So C, the locality for C will be worse compared with the first implementation. However, in this case, the gain coming from B matrix outweighed what we lose for the C's locality. And as a result, changing the loop order for B will reduce the latency from 24,000 milliseconds to roughly 2,000 milliseconds. Okay? Pretty significant speed up, 12x speed up. This is measured on Intel Xeon 4114 CPU, a server grade CPU. Okay, and this implementation is actually quite simple. We get the A, B, C, and previously we used ijk. Now our order is ikj, and here we allocate a buffer to. We need the actual buffer for the intermediate results. So this is showing the power of loop unrolling. Very simple change, couple of lines of code change, but it can make a very big difference. So to help you make a deeper understanding, we prepared the full starter code. So this is a snippet of the code to help you understanding, but the full code Actually, we'll put it here. Then we'll come to check it out. It's compilable. You can simply compile it and run on your laptop to give it a try. Okay, so that's using loop array ordering to speed up the matrix multiplication. Second technique, loop tiling. Okay, so the cache size is limited. So we want to optimize the locality by partitioning a big loop into several smaller loops. So what if the data is much larger than the cache size, which is usually the case, right? The cache may be a few megabytes, maybe 10 megabytes, 100 megabytes, but the matrix could be much larger, like 4K by 4K. That's very standard size. Even larger size is very common. So the cache miss will be pretty large if the data cannot fit in the cache. So loop tiling basically partition the loop iteration space. You can use several smaller blocks to iterate over, okay? And we can fit the working set, fit what we are going to access within the cache when we are choosing the size of the granularity of the blocking, okay, of the tile, of each tile. For example, this is our example, baseline, simple naive implementation of a matrix multiplication. The number of elements in A, B, C is all n squared. Right? So the access elements in the B matrix is n squared. That's could be pretty large. But we want to ensure the data can stay within the cache until it's reused. So what we can do is rather than accessing n squared memory footprint for the B matrix, here we want to tile it. Rather than n squared, we want to do n times the tile size, okay? N times the tile size. But we want that to be our footprint. So we can tile it by adding one more for loop right here. Previously, there are 3 for loops, I, J, K. Now, how many for loops? We have 4 for loops here, okay? I, J, K, and also there is a J, T, J tile. Okay? We added one more for loop in the outer dimension, where Tj equal to tile size. We also changed the range, okay, for the J, so that it only cover the range of tile size. And then here we skip every tile size for each iteration. So by adding a 4th for loop, we can tile the B matrix such that the memory footprint gets smaller. Can we do even more tiling? What if B times the tile, what if n times the tile size is too big? So rather than n times tile size, we want to have a footprint of tile size squared. So what we do, rather than 4 for loops, ijk and jt, we want to do ijk, jt, and kt. Add one more for loop to further tile not only the j dimension, but also the k dimension. So not only the j dimension, but also the k dimension. So the memory footprint for B would be tile size squared. And the memory footprint for A, since we are tiling the j dimension, the memory footprint would be n times the tile size. So compared with the baseline 3 for loops, now we have 5 for loops. So we also wanted this one, the footprint here, to be tile size squared. So we can do one more level of tiling. So let's see. Previously, we have 5 for loops, A, I, J, K, JT, and KT. Now let's add one more for loop, IJK, JT, KT, and IT. And we tile on all 3 dimensions. So the access memory footprint for A, rather than n times the tile size, n times the tile size, now it becomes tile size squared. So now we are done with all the 3 for loops. We tiled them. and their size is t, right here. So now what is the elements access memory footprint for A, B, C? Previously, they are all n square. Now they are all tile size square. How do we determine the tile size? We want to make sure the tile size square, which is the memory footprint for A, B, C, the tile size square can fit the cache, right? Such that we want to determine the tile size such that tile size square can fit the cache size. And if that is the case, we can reuse data. Since you're already there in the cache, then we can just iterate with whatever you have without having to load new data. So that's the magic for loop tiling, helping us improving the memory locality and also reduce the cache miss. What if we have multiple levels of cache? So here we just assume we have a single level of cache. We want to make sure tile size square can fit in the cache. What if we have two levels of cache? We can add another for loop to another level of tiling, right? So previously here we are doing IJK, IT, KT, JT. So this is one level and one level of tiling. We added 3 for loops. Actually, we can add one more. Okay? Tile 2. Then we have tile 2 size. We do multi-level of tiling. So we can make sure the tile size square can fit in the L1 cache, and tile 2 size times the tile size can fit in the L2 cache. Okay, so that's way how we handle the multiple level of caches. Just add one more for loop, add one more tiling. So here is how we implement that in real life. Feel free to check out the whole code in this link. It's compilable. So this is the 6 for loops we tiled in the IJK dimension. These are the original 3 dimensions. And before the tiling, the naive implementation takes 24,000 milliseconds to implement on CPU. But after tiling, it's 19 times faster. It's 1,200 milliseconds. So feel free to download the code and try it on your laptop. Okay, so we talk about loop reordering, we talk about loop tiling. Now let's talk about loop unrolling. So in processors, we want to reduce those branching overhead. You know, if your branch prediction is wrong, you have to squash a lot of instructions, as we learned in the computer architecture class, right? So branching is very expensive. So we want to minimize those branching overhead at the expense of increasing the binary size. Now, why is that the case? Let's see an example. So first of all, where does the overhead coming from? For example, when you have a for loop, at the end of the for loop, every time you have to test whether the loop index is within, is it out of the bound? If it is the case, we have to jump, right? That will introduce the branch prediction. The branch predictor is not 100% accurate. If it is not accurate, it will squash waste a lot of cycles. So we can reduce the overhead by loop unrolling, replicate the loop body by several times. So within this loop body, you don't have to have any branch instruction. You can just sequentially execute until you reach the end of the for loop. But you can imagine that will result in a lot of duplicated instructions, which will enlarge your binary size. So this is our simple baseline model, baseline code. Let's see, what if we unroll it by 4 times? Previously, we have IJK from 0 to n. Now we replicate it by 4 times. AIK plus 1, AIK plus 2, AIK plus 3. We explicitly write those indexes, adding them up, replicating the for loop without having to do any branch instruction. Okay? No branch instruction here. But here the step, previously we increment the pointer by 1, now we increment it by 4. Okay? That's why we are unrolling it by 4. So what is the consequence right? So the arithmetic operations for pointers is reduced by 4 times, okay, reduced by 4 times. What about the number of loop tests? Loop tests happens at the end of the loop. Right? Previously, every 1 instruction, you have to do a test. Now, every 4 of them. So reduced by 4 times. What about the code size of the inner loop? Previously, you have 1 instruction. Now you have 4 times the instruction here. So the code size becomes 4 times. So that's the trade-off. No free lunch. So this is the example. Again, you can download the code here. So we are unrolling the J dimension by 8. Also unrolling the K dimension. So we just replicate the code for AIK plus 1, K plus 2, K plus 3, and also J and J plus 1. We explicitly write them out. And this is quite helpful. Previously, without loop unrolling, it runs 24,000 milliseconds. Now it's only 8,000 milliseconds. Question. Right, you have to ramp up and also ramp down. So you have to take care of the case where the size of the for loop is not multiples of your tidying size. But usually in neural networks, the dimension is the 2 to the power of something. So it might be easier, not difficult to unroll. Question. So basically, these techniques, advanced compiler already includes this. So this is what we are learning how that works. A lot of them are already being taken care by the compilers. However, the compiler optimization may not be good for all matrix dimensions. So you have a particular matrix dimension, you will see usually hand optimization will be faster, especially those tall and thin matrix versus this short and fat matrix. All right, the next technique, SIMD technique, which is also quite useful. You will find it super useful when you are doing Lab 5 to implement the Llama 2 on your laptop using the SIMD instruction, okay? Single instruction, multiple data programming. So let's first give an overview of the instruction set architecture, which we learned in the computer architecture class. So the ISA is actually the interface between the software and the hardware, right? In abstract, give you an abstract of the computer by defining how the CPU is controlled by the software. So here we have several examples of ISA. Add 2 numbers, compare which one is larger, jump to a particular address, condition jump if some condition is met, load from memory, store to the memory, and I/O instructions. So this is the handshaking point between the software and the hardware. And there are 2 kinds of ISAs. One is the CISC, one is the RISC. CISC, the C stands for complex, a complex instruction set computer, like Intel x86. It has many specialized instructions versus the RISC, reduced instruction set computer, which has more efficient implementation. It's also shorter, like ARM and RISC-V ISAs. So here is the example of performing a single add. The CISC may need only 1 instruction versus the RISC may have 4 instructions. You have to first load 1 operand, load another operand, add them together, and store it to the memory. So what we learned in the 6.191 class, each instruction just operates on 1 piece of data, right? But if you think about matrix multiplication or convolution or neural networks, they are embarrassingly parallelizable, right? Many of the elements within an array, they are computed lockstep. You can easily parallelize them. So instead of just using 1 instruction to operate on 1 piece of data, can we use 1 piece of instruction to work on multiple pieces of data? So that's the idea of SIMD. For example, in this figure, there's a single instruction, single data. One multiplication instruction work on a single precision A and single precision B, versus a SIMD instruction. You also have the same one single instruction, but now you work on 4 numbers. Okay? Each one of them is 32-bit floating point number. Altogether, the register is 128-bit. So how many floating point it can fit? It can fit 4, right? We can fit 4 operands in A, 4 operands in B. We just execute one instruction, and now we can work on 4 pieces of data. So such register is called a vector register. We compare it with a scalar, called it a vector register, and hold and process multiple data elements. And this operation is called a vector operation. Okay? Basically, they work on the entire vector register. So with such SIMD programming, we can easily increase the computational throughput and speed and increase the energy efficiency, since decoding the instruction has overhead, right? It's not free. Now you decode one instruction, but you can process it on multiple data. So we amortize such instruction overhead. Okay, so this course is supposed to be very practical. So we introduce 2 kinds of SIMD programming intrinsics. One is from x86. One is from ARM. Okay, for an x86. Let's see what is a conventional approach. For example, single instruction, single data. We want to do a dot product of 2 arrays. Okay, and so AK plus times BK, and the cumulative is C. They do a dot product. With the Intel SSE intrinsics, so the step size becomes n divided by the range previously was from 0 to n, now it's from 0 to n divided by 4. Okay, what we are doing here is multiplying from these 2 registers, and every time we increment k times 4. Okay, and what are these? So load PS, means multimedia, because multimedia application usually have a lot of parallelism capability. And we can do parallel SIMD programming for them. Load here just means here load mul add means load multiply add, and PS here means packed single precision. Okay, packed single precision. So again, go back to our example. We are doing the multiplication on the packed single precision by loading from A and loading from B. And across different iterations, we are actually k times 4, starting from 0 and then 4 and then 8, step size of 4, because each time we are processing 4 elements using a single instruction. Okay? And altogether it's 128-bit. Each of them in single precision is 32-bit. We have 4 of them in the register, so altogether we are operating on 128-bit using the single instruction. Loading operand A, loading operand B, and then finally multiply them together, and then add it to C. So on the ARM architecture, we have the same instruction, but the name is different. Here, we load 1Q, so V means vector. It's a vector operation on vector registers. And load, multiply, add. This 1 is the number of the vector. And Q means quad word, meaning every quad means 4, right? So meaning we can operate on 4 words in a single instruction. So this dot product becomes we load 1Q of 32 on A, on B. After we load them, we multiply them. Finally, we add it, sum it up to the C address. Okay. So this is comparing single instruction, single data. This is single instruction, multiple data. So this is the full code of speeding up matrix multiplication using the SIMD intrinsic. It looks difficult, but it looks very complicated, but it's actually quite simple. We just need to look at half of them. This is the x86 version. This is the ARM version. We can just look at the first one. So again, we have 1, 2, 4 loops, 3 for loops, okay, 3 for loops. Here we are going to create a accumulator, okay, that is 128 bits, okay. And then the result will be we first load from A, load the transpose version of B, and then add it back to C. And here we are processing 4 elements at a time. Therefore, here K plus equal to 4, since the vector size is 4. And finally, we call this multimedia add PS to accumulate the elements in the accumulator. And on the bottom is the ARM version of that. It's pretty similar. Increment by 4, load A, load B, multiply, and finally accumulate them together. Okay, so that is in D. And next, we are going to switch gear to talk about multi-threading. We are also going to exploit this technique to implement Lab 5, which is concurrent execution of multiple threads within a single process. Okay, so this is the basic programming model of a shared memory programming. This is a single-threaded process versus a multi-threaded process. Let's see what's the difference. Okay, so we can see the multi-thread process. They share the same memory space, the code, the data, for the open files, but they have their own registers and stacks, program counters. Okay? And different threads can also run on different CPU cores, improving the performance by allowing parallelism. And the multi-threading can have several advantages. For example, improved performance. Multiple threads can execute a task simultaneously. If one thread is blocked by disk IO, waiting for the IO to complete, the CPU can do context switch to another thread. And that can increase the resource utilization by minimizing the time of waiting for some resource. For example, here, this is across different times. This is across different threads. You have thread T1, T2, and T3. The blue part is when the thread is allocated on the CPU. And then here it's going to do context switch to another thread. For example, if thread 1 is blocked by this IO, it can work on thread 2, etc. So minimize the waiting. If you have so many threads, basically you can have very CPU core. Assuming that someone is waiting, then we can schedule another thread. That's basically the principle of the GPUs. So we want to break down the complex problems into simpler and smaller tasks. So for example, in matrix multiplication, we can use one thread, individual threads, to deal with individual blocks by blocking a larger matrix into smaller matrix and assign one thread for each smaller matrix. So in practice, there are very convenient programming models and libraries for shared memory multi-thread programming. We introduce pthread and also the OpenMP. So pthread is a C library for creating and managing threads. So let's go to our classic example of matrix multiplication. Let's brainstorm a little bit. When we have this matrix multiplication, how do we divide the work? Say we have n threads, and we can just naively divide it according to the rows. Since we are multiplying the k dimension, we can just divide the ai dimension. Okay, thread 0 is responsible for the first chunk, and then thread 1, the second chunk, all the way to thread n. And each of them is multiplying the partial A matrix with the B matrix and write it to the partial C matrix. So different threads don't have to communicate. They're sharing B, but their input output, they don't interfere with each other. So that's a very easy divide of the workload. And basically, the code has two sections. One is the overall coordination among all the threads. The other is for each thread, what is it going to do? Okay. So for the overall coordination, we first create the thread by calling pthread t threads, and then specify the number of threads we want to create. And then we are going to assign the workload. Okay, so here we are going to create the threads by giving it the address and also what it's going to do. What it's going to do is basically this matmul multi-threading function, which is actually defined by ourselves right here, matmul multi-threading. So once the thread is created, it's going to run this function. We're going to talk about that. And later, we have to wait for all the threads to complete. Some of them may complete first, some of them may complete last. We have to wait for the last one to finish by calling pthread join. Make sure all the threads arrive at this point. So that's all. That's the overall management, creating the threads and also assigning the work. So what are they going to work on? So here we are going to specify the function that each thread needs to execute. This is matmul multi-threading. So we are going to indicate the starting and end row for each thread. Since we are dividing the work by the rows, thread 0 is responsible for the first part, dividing by the row, thread 1 and the thread n. Each thread is going to have a thread ID. So we can easily divide the work by telling the start row will be thread ID times the row per thread. And end row would be thread ID plus 1 times how many rows per thread. But if you have 10 rows per thread, thread 0 will be 0 to 9. Thread 1 will be 10 to 19. Okay, start row, end row. And then each thread can only conduct one part of the matmul using these 10 rows only. Okay, so it's going to I is from the start row to end row, and this is the B matrix right to the C matrix. And the inner part is the very simple 3 for loops. So this is speeding up matrix modification in multi-threading. In the homework, feel free to come up with more creative idea to break the workload. We can divide it by A or can have other ideas. So by using just this simple implementation, let's see the speed up results. But in naive implementation without multi-threading takes 24,000 milliseconds. But by using 4 threads, it actually depends on your CPU, how many threads you have. It has 5,800 milliseconds. Okay, 4 threads, 4.1x speed up. A little more than linear, maybe due to better utilization of the memory, the cache. Okay, so it's actually a very effective technique to accelerate matrix modification. So if pthread looks very complicated, we introduce even simpler programming model using OpenMP. Okay, it's very portable, same program can run on many different operating systems and different hardware platforms. The way it implements is that it has many compiler directives, okay, like this pragma OpenMP parallel to create a parallel region. And you want to specify which for loop you want to parallelize and which section you want to parallelize. And it has very simple synchronization, intrinsics, OpenMP, single, critical, and barriers. And also you can easily set the number of threads by calling these interfaces. So the parallelization of a matrix multiplication in OpenMP is very simple. Actually, you first specify how many threads you wanna use, set the number of threads used in the parallel region, and you wanna specify here is the parallelized region. Okay, this is a pragma OMP parallel for, indicating we are parallelizing this for loop, which is the I dimension. I dimension is right here, so it's chunking, tiling the A matrix in the row dimension. Okay? So this is very simple implementation compared with pthread. So the code of using OpenMP is actually much cleaner than that of using pthreads. All right, let's take a 5-minute break before we jump into CUDA programming. All right, welcome back. So let's continue and talk about CUDA programming. The interesting part is yesterday the Nobel Prize was released. Actually, both of them are related to GPU computing, right? AlexNet, Hinton, and also AlphaGo, they're all trained by GPUs. And CUDA programming is the fundamental of that. So let's see. So that could be a good motivation for us to learn about CUDA programming. So the GPUs provide a much larger throughput and memory bandwidth. It has a very unique programming model. CUDA was introduced by NVIDIA in 2006 as a general purpose computing platform and programming model by leveraging the massive parallelism for compute and also the memory footprint and memory bandwidth. It's a C-like language to express programs that run on the GPUs. So CUDA programming is based on a hierarchy of CUDA thread. Okay, so here we have two levels of hierarchy: a grid of blocks, thread blocks, and also and each thread block has many threads. So in this example, we have 2 by 3, a grid of 2 by 3, and a block of 3 by 4. So altogether we have 72 CUDA threads. So the thread ID could be 3-dimensional, which is very natural for handling n-dimensional arrays. In this example, it has 2 dimensions. Okay, so we first specify the number of nx to be 12, and ny to be 6. That's probably the size of the workload. And then we create 4 by 3 threads per block. Okay, so 4 by 3 threads within each block. And the dimension of the block will be the dimension of the workload divided by the threads per block in x dimension. And the workload of y divided by the threads per block in the y dimension. Okay. And then this call will launch 72 CUDA threads by calling matrix add, specify the num blocks, which is here, and specify the threads per block, which is defined here. This single line of code will call 72 CUDA threads at the same time, which consists of 6 thread blocks and 12 threads in each block. So let's continue. So here we are launching 72 CUDA kernel calls at the same time. So launch many CUDA threads, and on each thread is going to execute this function. Okay, so this is the device function. Device means this piece of code runs on the GPU versus this piece of code runs on the CPU. Okay? So the name is matrix add. What it's going to do is, according to the block ID x and times the block dimension, the x dimension, and plus the thread ID x, okay, it's going to tell you where am I? I am a thread. Okay, which part of the matrix am I going to work on? So that's specified by the index I and j according to the thread ID and also the block ID. Since it's two hierarchies, I'm going to know where am I going to work on. So I'm going to work on I and j, specified by these 2 sentences, and then I'm going to work on AJI, BJI, and add it to CJI. So each thread is going to compute its own workload specified by the block ID and the thread ID. And since different threads has different IDs, they are going to work on different part of the workload in parallel. So that's where the parallelization comes from. So memory model is quite important since compute is cheap, memory is expensive, and let's look at what is the memory model for GPU programming. We have distinct host and device address spaces. Host means on the CPU, device means on the GPU. They have different address spaces. Okay, so the data can be moved between the host and also the device. So give an example on the bottom. We first create an array on the CPU. Its name is A, and then we are going to call it CUDA-malloc to memory to allocate the memory on the GPU by specify which device and how many bytes. Okay, so now this device A, this address will have be allocated with this amount of memory. Okay, so we allocate a buffer in the GPU's address space, and then we are going to move data to this address. So device A is the address on the GPU, and A is the address on the CPU. Now we copy the data from CPU to GPU by calling CUDA-mem copy, by calling from CPU A to the GPU address device A. This amount of bytes, the direction is mem copy from host to device. Okay, you can also do device to host. So this is the memory copy. So we allocate the buffer in the device and then copy the data back and forth from the device to the host or from the host to the device. However, we cannot directly access the value in the address space of the GPU. So access device A from the host will be invalid because device A is not in the host address space, but is in the device address space. So there are three distinct types of address spaces visible to the kernels. We have the global memory, which is readable and writable by all the threads. We also have the per block shared memory, which is readable and writable by all the threads in that block. We also have the local per thread private memory, which is even smaller, that is readable and writable only by that thread. So different address spaces defines different locality and different load and store overhead we have to take care of. Okay, so given that, we can jump into how to speed up matrix multiplication. Okay, so compared with the CPU implementation, which takes 24,000 milliseconds, the CUDA implementation on the 2080 Ti GPU, which is quite outdated actually. The CUDA kernel is only 6 milliseconds, and the overall MATML takes 200 milliseconds. That's almost 100 times end-to-end speed up. And actually, you can tell from here, launching the kernel is very expensive. The kernel call itself is only 6 milliseconds. So we want to minimize the amount of kernel calls and do as much as possible within the kernel. In neural networks and large language model inference, this is very widely used called kernel fusion. You want to fuse the prelog, the epilog, for example, the activation function to fold it into the actual matrix multiplication kernel, okay? So that you don't have to have such a large overhead. You amortize overhead. You launch one kernel, you compute as much as possible, not only the matrix multiplication, but also the activation functions. That's called kernel fusion. And now let's see what it's doing. So each block is working on a portion of the matrix. Okay, so we are going to tile the matrices so that each thread is only responsible part of it. So we do a per block allocation for tile A and also tile B. And then according to its thread ID in the Y dimension and also X dimension, and also the thread ID, a block ID in the X dimension times the tile size, we can specify which part of the A matrix we are responsible for. So only a chunk of the A matrix. And then we are going to wait for the memory loading since each thread is responsible for loading only one part of this block. We have to wait for the memory loading to finish before we can do the tiled matrix multiplication. Okay, so we call sync threads right here, and then we are going to multiply these two elements together and add it back to the value. And after every thread finish such operation, we are going to write this value to the corresponding location. So recently, since the tensor application is getting so popular in deep learning computing, NVIDIA invented the tensor cores, which has even higher throughput and more data types, especially low precision data types. So on a CUDA-Core platform, we can have one FP32 or two FP16 multiply and accumulate in each cycle. Well, a tensor core can finish an entire matrix multiplication, which is 4x4x4 for Turing architecture, 4x8x4 in Ampere architecture, in FP16 in each cycle. So in one cycle, you can finish the entire matrix multiplication. So the throughput becomes much larger. And if the precision gets lower and lower, like into 4, you can see the tensor core throughput is even higher. So this is on the H100, the measured throughput compared with, here is CUDA core P32 67, and this is, here is the tensor core. One is P16, one is TF32, and here is the tensor core in FP8 or int8 or sparse FP4, sparse FP16. Okay, it's much higher, actually 60 times higher throughput compared with the CUDA core. And here is comparing when you have different workload sizes. By workload size, we mean the dimension of the matrix multiplication, n by n by n matrix multiplication. As n gets larger and larger, the speed up between the CUDA core and tensor core, between CUDA core and tensor core, the gap is getting larger and larger. So tensor core is very good at processing these large matrix multiplications. So here up to 3.8 times faster compared with the CUDA core. So the basic intrinsic is the matrix multiplication intrinsic called MMA. Okay, so here we can show an example to compute the 16 times 16 by 16 times 32 MMA using 16 by 8 by 16 intrinsics. Okay, so this is showing how can we use small intrinsic to compute on large matrix multiplications. Like in Llama, we can easily have like 4K, 10K, those large matrices. But our intrinsic is small. So how can we leverage those small intrinsics to work on large matrix multiplications? So the first step is to break down the input and output into 16 by 16 and 16 by 8 tiles. So 16 by, since the intrinsic is 16 by 8 and 8 by 16. And then we can process each tile sequentially. Right? Tile 0 by tile 0, tile 1 by tile 2, tile 0 by tile 1, and then tile 1 by tile 3. Okay? So we just call the intrinsic several times to process a larger matrix multiplications. So the order of applying these 4 MMA intrinsics does not matter. All right, so that concludes our section 2. Now let's switch gear to section 3 about inference optimizations. So to enhance the compute speed and reduce the memory usage, in the previous lectures, we talked about several techniques like pruning, quantization, neural architecture search, distillation. They are not function preserving, right? So they change the workload. Here are the techniques that is function preserving. The convolution remains a convolution. A 3x3 convolution remains a 3x3 convolution. It's mathematically equal. but we can have different implementations, and they result in very different efficiency difference. Okay, so we start by talking about image to column convolution, a very efficient and simple implementation of convolution. And then in place steps-wise convolution, since steps-wise convolution is quite widely used in mobile net architectures, right? So how to efficiently implement that is crucial. And then we are going to introduce NHWC or NCHW different orders to represent different convolution, like point-wise and depth-wise convolution. They prefer different memory layouts. And finally, Winograd convolution, by reducing the number of multiplications, at the same time, it remains mathematically equal. Okay, so let's first talk about image to column convolution. So as we have seen, matrix multiplication is a very basic, intrinsic for very basic building block, right? But convolution is a little different from matrix multiplication as 6 for loops rather than 4 for loops. So the question here is, rather than 3 for loops. So the question here is, how can we use matrix multiplication to implement convolution? And how do we exploit GEMM, generalized matrix multiplication, GEMM, to implement convolution? So image to column is a very common technique. So here we have the input activations, and we have 4 kernels here, and we have 4 output channels. So here we can have the expand the input activation from ABC, F, G, H, K, L, M. They all convolve with kernel 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So we lay out the memory in this way: A, B all the way to M, B, C all the way to N, which is A, B all the way to M, and then B, C all the way to N, which will be multiplied with kernel 0, 0, 1, 2, 3, 8, which is right here, 0, 1, 2, 3, 8, right? Such that we can have this row multiplied with this column. So blue, green, yellow. And also here is blue, green, yellow. Okay. So we lay them out in this way, we can turn a matrix multiplication to implement convolution. So the dimension here is k squared c. If k is 3 by 3 kernel, this will be 9 by c. And here is also 9 by c. Okay, so 9 elements in one kernel, and we have c number of kernels. Okay, so that's how do we use convolution, matrix multiplication to implement convolution. The pro is that it's very simple, but the con is that it requires additional memory usage. For example, we have a lot of duplication from ABC, FGH, KLM versus BCD, GHI. We have 6 elements that's overlapping with each other. So that's the drawback. Additional memory space. But this can be optimized by using implicit jam to solve the additional memory problem. Okay, so we directly operate on the input weight and activation tensor without having to lay them out, physically lay them out and materialize them in the memory. Okay, so the next optimization is in place stepwise convolution. So stepwise convolution is very widely used. For example, here it has 3 components: 1 by 1 count 2D, 3 by 3 stepwise count, followed by 1 by 1 count 2D. And each channel is operated independently. By independently, we mean the channel 1 is only related to input channel 1. Channel 2 is only related to the input channel 2, and similar for channel N. So if you use naive implementation, we have to allocate double size of the CHW, okay, H, W, and then C channels. We have input, we have output. So the total memory footprint will be input plus output, which will be 2 CHW. So what we find in this MSUNet v2 paper on the bottom here, we find we can do in-place stepwise, which is basically allocating a temporary buffer. And then when we are working on the first channel, we write it to this buffer to the compute. And then we write it back to the first channel. When we are computing on channel 2, we also use the same temp buffer and write it back to channel 2, channel N, etc. Right? So in this way, we don't need any large, by doubling, we don't need to double the memory footprint, but don't only need the constant, which is one constant buffer. So 1 plus C times HW. Previously, it's 2 times CHW. All right, next optimization. The memory layout matters a lot, so we are going to compare the NHWC and also NCHW memory layouts. And which one of them is good for convolution, depth-wise convolution versus point-wise convolution. So these are all about data layout and memory management, since data movement is super costly. As a principle in computer architecture, we want to minimize the data movement. So how to allocate the data becomes super important. So the first slide is about we should use NHWC for point-wise convolution. What does that mean? So this is the input activation. Height is 3, width is 3. We have 10 channels in this case. NHWC means the inner loop is the C channel. So we are storing 0, 9, 81. They are contiguous in the memory. Okay, and the weight we combine it with the weight, which is since it's point-wise convolution, it has only 1 by 1 in the XY dimension. And let's compare the NCH versus NCHW versus NHWC. What does this mean? N is the batch dimension, C is the channel dimension. Here we have 10 channels. H is the height, W is the width. So here we have height and width in the inner loop. So the layout would be 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11. So that's the NCHW layout. Versus if the channel dimension is in the inner loop, what's going to happen is we are going to store 0, 9, 18, all the way to 81 contiguously in the memory. Okay, 0, 9, 18 contiguously in the memory. And then the second channel, which is 1, 10, all the way to 82. Okay, so if we use the NCHW manner to perform 1-by-1 convolution, which needs to access 0, 9, 81, 0, 9, 18, 27, 81. There's a lot of not discontinuous memory access, right? So it's not efficient. But if we store them in NHWC manner, the channel dimensions are laid out in the memory sequentially. So we can take advantage of a lot of cache hits. So that's why NHWC. The C channel in the inner dimension is very good for the point-wise convolution. But for depth-wise convolution, the story becomes totally different, right? So the kernel is also into this is the kernel for the weights. We have 10 channels, and this is the output activation. We have a temporary buffer. Okay. We first come out with the green channel. Okay. If we use NHWC, C channel in the inner dimension, we have 0, 9, 18, 81, 0, 9, 18, all the way to 81. They are continuous. But if you use NHW, everything in green will be laid out first, and then red, and then gray. So for depth-wise convolution using NHWC, there will be a lot of discontinuous memory access for the red. And then for the NCHW manner, the memory access will be continuous. Okay. So for depth-wise and point-wise, they actually prefer very different memory layouts. Any questions so far? Okay, if not, let's watch the animation again to get a deeper understanding about the sequence, which really matters about the locality and also the memory footprint. Okay, so finally, let's take a look at Winograd convolution to replace the number of multiplications and to speed up the computing. So here's an example of computing a output with a 3x3 kernel, interact with 3x3 input. We can move it in the horizontal and vertical dimension to produce 4 different outputs, R0, R1, R2, R3. Okay. So how many max is needed to produce 4 outputs? So for every output, we need 9 multiplications, 3x3, 9 multiplications. Another 9, 9, 9. So altogether 4 times 9 times C, since we have the C channel dimension as well. So 36 C max to produce 4 outputs. What if we have a magic transformation? So we transform this data, assume it's free. Let's look at how it's implemented later. Assume this transformation is free. Become a 4x4 by C tensor, and the 3x3 filter becomes 3x3 by C. Transform the filter, and then we just do pointwise multiplication. That's only 16 multiplications to produce an intermediate output, and then we assume we have a free output transformation. We can get this 2x2 output tensor. Okay, so in this case, we only have 4x4 by C, okay, which is 16 C max to produce 4 outputs, which is 2.25 times fewer max compared with the direct convolution. So that looks pretty exciting. What does the data transformation look like for the input, for the filter, and for the output? Actually, Winograd convolution give several magic matrices to do such transformation. Okay, so we do the filter transformation. This is the filter, and this is the input. We do the data transformation offline using the G and B matrix. So this is the G matrix, which is only consists of 0, 1, 1 over 2, minus 1 over 2, which can be easily implemented by shift. Okay, 1 over 2 is basically shift by 1 bit. And this B transformation matrix consists of only 0 and 1 and minus 1. Okay, so no multiplication is needed. Here, no multiplication is needed too. Only shift is needed. And output transformation, the A matrix. Okay, this is the A matrix. Only 0, 1, minus 1. No multiplication is needed too. Okay, so that's why the total number of multiplications is reduced from 36 to only 16. 4 by 4, 16 element-wise multiplications. And this paper, fast algorithms for convolutional neural networks, proves the result is the same. So feel free to implement it yourself. Very simple. Actually, you can test this equation in a very simple prototype by putting these magic transformations. One for the kernel, one for the input, one for the output. All right, we're pretty much there. So by combining these techniques, we can deploy a large language model locally on a laptop, which is using the TinyChat engine, which is the efficient on-device inference library. You can deploy a Llama 2 or Llama 2 7B, Llama 3 7B, and 13 locally on this laptop by using after quantization, which we are going to learn later. TinyEngine also supports the on-device object detection, person detection, visual wake words, which We saw the demo in the last lecture, so it's all open source. Feel free to give it a try. When you are implementing Lab 5, whenever you encounter any difficulty, feel free to check out the TinyEngine repo, which has a complete implementation for the inference engine for large language models. So in Lab 4 and 5, we are going to first quantize the LM to 4 bits using the AWQ technique, which we are going to introduce a few weeks later, and also deploy a large language model by using the TinyLM engine to run a local chatbot on your computer. So including the techniques we learned in this lecture, like loop unrolling, reordering, SIMD, multi-threading. Okay. So here's the summary of today's lecture. We talk about microcontrollers, the resource constraints, and critical factors limiting why it's difficult, including both memory and also compute, and why data layouts is very important. For the optimization techniques, we introduced loop optimization, like loop reordering and tiling, and also the blocking, and also multi-threading techniques, SIMD techniques, CUDA programming, image to column convolution, in-place stepwise, HWC and NCHW, finally, window-wide convolution. All right, that's all for today. Thank you for your attention. We'll see you next Thursday, since next Tuesday is a holiday for students. Okay, have a great long weekend.